So I just started the recording.
Okay. Got it. So I guess I'll start now.
Sure.
Hello, everybody, and welcome to the virtual seminar series for the SIG on AI and machine learning in security. We are part of the TCCN, or the Technical Committee on Cognitive Networks of IEEE ComSoc. So I am Professor Subha Subbalakshmi. I am a professor at Stevens Institute for Technology, and I am the founding chair of this group. And Dola Saha is our vice chair. She's from SUNY Albany. Today, I'll just do a quick introduction for the group, where we are now, the seminar series, and then I'll hand it over to our speaker today. If I can move the slides, there it is. So as of now, we are about 350 members in the LinkedIn group. You can actually find us in LinkedIn if you want to join us. You can search for SIG AI ML Sec, or you can just email either Dola or me. We usually use the LinkedIn group as a means for communicating with our group, which is now pretty big. And we're looking for widening the engagement of the group in the main activities. So you should see some more announcements in the LinkedIn page regarding that. Pretty soon, we expect also to have our own email blast for this group, for the SEC group. And you should hear about that as well pretty soon. And then we can take that forward. Literally 1 year ago, this is our first year anniversary. We started this seminar series as a sort of response to the pandemic and the trouble we were having to get people physically in our group to talk. So we've got a pretty impressive line of speakers so far, kicked off by Professor Winspoor from Princeton on November 17th, 2020. And today we have Danijela Cabric, professor at UCLA. So I will quickly make an introduction. Before we go on, before I introduce Danijela, I just want to make quick announcements about the talk itself. Everybody is muted on entry. Please stay muted throughout the talk, but do feel free to type in questions as and when they show up in your minds for the speaker to answer. You can use the chat box to do that. We will read these out at the end of the talk, and then Danijela will address them. So please feel free to use the chat box liberally throughout the talk. That doesn't affect the talk per se. So today's speaker is Professor Danijela Cabric. She is talking on open set wireless transmitter authorization, deep learning approaches and practical considerations. Danijela is a professor in the ECE department at UCLA. Her research interests include novel radio architecture, signal processing, communications, machine learning and networking techniques for spectrum sharing, 5G millimeter wave, massive MIMO, and IoT systems. Dr. Cabric received the Samueli Fellowship in 2008, the Ottawa Foundation Research Grant in 2009, the Hellman Fellowship in 2012, the NSF Career Award in 2012, Qualcomm Faculty Award in 2020 and 2021. She's also an IEEE Fellow, and her research on deep learning-based RF transmitter fingerprinting is supported, I'm guessing, by NSF. I've got this panel blocking me, so I'm unable to read it. But she has a very impressive body of work, and I'm really looking forward to hearing her talk today. Welcome, Danijela. And take it away and stop sharing.
For the introduction, okay, let's just make sure that. Just need to go into slideshow mode. Okay, can everybody see my screen? Okay. Okay, well, thank you, Subha, for the introduction, and thank you, Subha and Dola, for inviting me. It's really a great honor to be a speaker at your anniversary. Today, I will talk about our body of work on RF fingerprinting, and in particular, this problem of open set transmitter authentication. And we're applying deep learning approaches for that, as well as based on the data set that we have collected. I'll talk more about that
what are the practical considerations that one needs to take into account. Actually, the presentation and the work actually presented here is done by my students, Samar Hanna and Samurdi Karunaran. Our lab is at UCLA called CORS, Cognitive Embedded, Reconfigurable Embedded Systems. And actually, you can find more information about our projects and papers at the link below. So I guess in this community, I don't have to really motivate the problem, but in particular for the Internet of Things, where we expect that there will be many sensors, actuators, and connected devices that will give us very valuable data, we believe that security is going to become a major issue, because we don't want for these sensors and devices to be tampered or maliciously sending the data, or even if they are failing, we want to recognize that. So the goal is really to authenticate them so that we can trust the data that they are sending. Now, how is the kind of security and data, device authentication handled? Well, so far it's very mature field, and from the wireless perspective, we can actually address the problem across the stack. So far, kind of software approaches that are using either MAC layer, MAC address kind of way of authenticating are very popular. However, they're easy to spoof. Now, adding cryptography and kind of approaches that are possibly more robust is quite complex, and we would like to address problems of low complexity, low power, possibly even energy harvesting type of sensors, so that devices basically don't have to do anything in order to be authenticated. So that brings us to the physical layer. And there we're basically going to use the inherent properties of kind of radio hardware on the transmitter side that kind of embeds what we call unique fingerprints that basically can be used to differentiate different transmitters. And in some body of work, channel state information is also part of the physical layer authentication. Now let's try to address the problem. So here we're assuming that the authenticator basically has a powerful receiver that can, and the processing will be done and authentication on the receiver using appropriate algorithms. And here we have a very large number of transmitters. They're going to send wirelessly the signal for the authentication. Authorized set is basically just a subset of these transmitters that the receiver knows about, and they have the permission, or they're the one that we're going to trust. And then in addition to these, there is basically a set of transmitters that are possibly, actually let me just do, that we can introduce in terms of understanding our problem of authentication, which I will call outliers, right? But those are the ones that we can either collect on our own, or they're kind of already through some other mechanisms recognized as either malicious, or basically they don't belong to the data set. So each one of them will send the signal to the receiver, and given their fingerprint, the authenticator needs to basically decide whether the signal belongs to the set A or it is outside. So again, this set K is something that we have proposed, and actually in recent literature, there are some other works that have shown that this set will help. Now we'll address the problem if we have the set K or not, but it's a very important concept that we are using. So first thing that the talk actually has 3 parts. The first one is trying to understand among the kind of open set recognition deep learning approaches, which one is the most appropriate for this problem of RF fingerprinting, and how this open set classification is going to, which one is going to be the best performing. And then if you remember this
set K of non-outliers is something that we have kind of considered further and try to synthetically generate outlier signals that can again be helpful in this open set authentication. And lastly, I will talk about some of the real-time performance issues, in particular when we have a set of transmitters that is dynamically changing. We're adding new transmitters, removing. How can we accelerate that without the need of retraining? So this is actually the last part of my talk, where we are using some new algorithmic approaches for authentication. So let's start with the first topic. First, I will kind of review what are the existing approaches for these passive physical layer authentication, and then we'll introduce our approaches, data set, how we've evaluated, and some results. So actually, if you kind of go through the literature, RF fingerprinting has been a topic for maybe the past 15 plus years. And this idea of using possibly IQ samples or recognizing frequency offset at the beginning of the packet has been explored through detection algorithms of kind of this hypothesis test, whether the signal belongs to the authorized or not. Now, the problem is that these handcrafted features, especially if the signal to noise ratio is very low, or number of samples you have is very limited, really are not performing very well. And also kind of extension to this work was recognizing possibly modulations of the signals and so forth. But then with kind of advancements in deep learning and their success in other domains such as speech processing and computer vision, there is this kind of new line of work on RF fingerprinting that is trying to apply deep learning and learn directly from IQ samples. And we are kind of falling into this category because there has been kind of evidence that there are actually quite credible tools to solve this problem. Now, one of the things when you look at the literature, majority of the work is focused on authentication from a perspective that we're just classifying transmitters, meaning that we actually have a data set that contains all possible signals that we are going to encounter. And then the neural network just needs to tell us which one is the transmitter, which we believe is actually practically not always, I mean, it might have some applications, but in reality, we could expect there will be some unseen and possibly malicious transmitters. And I will illustrate actually what's the problem with this classification approach. So let's try to visualize these differences in classification, anomaly detection, and open set recognition. So as I said, this kind of existing body of work assumes that we have data sets, and basically these circles are corresponding to samples of some authorized transmitters, and we have actually complete knowledge of them. And the goal is to classify them. Basically, when you see IQ samples from the orange transmitter, you basically say it's an orange transmitter. Now, the problem arises if we have some outliers, because this classifier has these kind of fixed boundaries. So these new outliers will be they will be classified as one of the authenticated, and basically that's our security threat. So now, anomaly detection, that's kind of another approach to consider outliers, is to effectively just reject unknown classes. So you're not trying to label the transmitters by color. And for example, here, I'm just going to say you're authorized or not. I'm not trying to say, for example, here, I won't be able to say it's a blue versus purple. And the goal is to kind of create these boundaries now to reject the anomaly. Now, open set recognition kind of tries to do something more than anomaly detection. And that is, in addition to rejecting the unknown classes, it tries to actually recognize or classify the known classes. So this is actually the problem statement that we are going to consider. So again, we're going to use IQ samples directly. And I mean, in this case, I'm showing 4 different snapshots of 4 different transmitters. And obviously the randomness of data, channel, RF fingerprints, it's very hard. I mean, doing it through signal processing, as I said, it's possible, but we believe that deep learning is really a great tool to extract from these high dimensional signals features that will be used to isolate the transmitters. And again, we will try to kind of address this as the sizes of authorized set are increasing, what happens when we introduce the known outlier set, and we also introduce some test outliers to basically find the performance of our method. So now, here are some of the questions that we're going to answer. There are many approaches for open set recognition and anomaly detection. So now, what are the appropriate methods to use on these IQ samples, and how well they will perform in transmitter authorization? Now, how this idea of using, if the number of authorized transmitter increases, can we maintain that performance, and which method is the most robust? Now, the question of adding known outliers that are kind of helping our algorithms understand that there are signals or transmitters outside of the authorized set. And there is also some initial work that we have done on impacts of when is the data captured. And actually, I'll talk about our current and future work in terms of what are the other practical considerations that one needs to consider when looking at this problem. So let's start with kind of an overview of open set recognition approaches that we have considered. So indeed, we have looked at 5 learning architectures. Here I'm showing 3, and next slide will outline the other 2. So the first they're basically all based on deep learning. So the first one we call a discriminator, and it's discriminator because it's actually just detecting whether the signal is authorized or not. So it kind of starts with these IQ samples. It uses a neural network to extract the features. I'll talk more about that. And then it has only one binary classifier with a sigmoid activation function that will basically give us a binary output. And this one doesn't require any, it does require known outliers, because the known outliers will help us differentiate the authorized or non-authorized. It doesn't classify within authorized set A, and it requires a threshold. Now, if you remember my open set recognition, indeed, I want to actually recognize the authorized transmitters. So this discriminating classifier, which is kind of enhancement of the discriminator, is, we call it a D class. Again, it starts with the same front end from IQ samples to features, and then it kind of has A+1 classifier that learns based on known outliers what are the classes. And we have A+1 cardinality of A, which is basically now I can identify each of the authorized transmitters and then recognize the outliers. And then again, we have a set K that is required. This one is actually good because it doesn't require a threshold, and activation function is softmax. The next architecture is similar. It's trying to kind of classify, but in a different way from a discriminator. Basically, from the feature extraction, goes into the binary classifiers and tries to kind of learn for each particular authorized transmitter whether the samples belong to it or not. So the binary classifier will basically tell us, it's going to be output 1 and 0 for a transmitter 1 from our authorized set, and so forth. So if outliers will not have a clear output on the binary classifier. Ideally, transmitter 1, for example, from authorized set, will have the first binary classifier say it's 1, the rest of them should be 0. The outliers are effectively confusing this binary classifier and therefore considered outliers. So this one actually can work without the known outlier set. And similarly, it can recognize each transmitter, as well as requires a threshold because of these binary classifiers. The other two architectures, one is actually OpenMax, which people, I mean, if you follow the literature in this field, it has been used before. And we are here using it just because we want to compare. So again, we're using this same algorithm for feature extraction. And then we are kind of in an OpenMax way now using this neural network classifier for our recognizing basically the transmitters from our known set. And this one does not exploit the outlier, known outlier set. And it can also, it doesn't also classify and doesn't require a threshold. And the last approach is the autoencoder. And it is kind of a classical autoencoder architecture. It doesn't, if we have some known outlier set, unfortunately, it cannot exploit it. It can classify and unfortunately relies also on a threshold. So now let me just give you a little bit of insight on what are these kind of building blocks of our algorithms. So we're using 256 samples, I and Q. So this is our input. And if you remember, there are feature extractions that we're using in this. Everyone but autoencoder is using the feature extractor that is basically built of residual blocks and these convolutional layers. So there is kind of a same architecture that's used on all of them. And then we have some feature processing through kind of dense layer and ReLU activation, and then followed by decisions. For example, if you remember, OVA has a set of binary classifiers that are using this sigmoid activation. Here is a little bit more details on number of parameters that we use. So disk, D-class, and OpenMax are very similar in terms of their kind of performance. And you know, I just outlined basically this part. The autoencoder here is kind of a detailed architecture in terms of input, output 256 by 2. We kept the same input size and built this encoder with, again, residual and convolution layers. So effectively, network architectures are very similar, and the key differences are in activation functions, if you remember, labeling and post-processing. Here is kind of the number of parameters that one would require to do that. And in terms of actually their sizes, they're about the same, like in the order of hundreds of thousands parameters. So now let's see how these algorithms perform. So first I'll introduce this data set. So what we have used to kind of, because I think if you're working in this area, you have to have real transmitter data, because modeling these hardware impairments is actually very challenging. We don't quite have good models of what really causes these imperfections. So what we have used is this Orbit testbed from Rutgers University that has actually a very large number of Wi-Fis that are mounted on the ceiling. There is a grid of like 20 by 20, and we have remotely activated 163 Wi-Fi transmitters, one at a time, and used for now, I'll introduce a new data set. This is actually what I have currently for the results. The data was captured with the USRP receiver. Every transmitter had a 1 second capture at 25 megasamples per second. And instead of doing IQ samples directly, we have actually processed the data to extract the preambles. Because in our prior work, we actually found that for the authentication, the randomness of just payload hurts us, and it's better to have a common data for the authentication. So since Wi-Fi has a preamble, we have extracted it and used it for authentication. The signals were captured over 5 days. And why did we do that? Is because we wanted to actually understand this impact of variability, both channel as well as fingerprints. So 4 days for training, and then we had a same day test from these. So basically we test on the same day we train, but then we also did a completely new day for testing where we don't have any training data. And I'll show you what is the impact of those. Okay, so in terms of data, we actually had lots of data, and I'll talk about that data set again. Out of 163 transmitters, we have kind of done these partitions into authorized set, known outlier set, and then true outliers, the ones that we have never used in training. And then just to kind of have data that's better generalized, we have done these 10 times. We have partitioned this data in 10 different ways. And how are the signals divided? Well, if you remember, we had 5 days. So for days 1 through 4, we are using them for training. And then this 5th day is if we want to actually use completely new data only for the test. So this is only for the test. But for the training, we could have a same day test, meaning the data is the networks are trained on same data and tested on the same data. So we did 30% same day test and then 70% for training. And then these known outliers are actually not used in test. They're only used for training to help us build a good classifiers, and outliers are either all used for testing. Actually, this is because outliers are not used in training effectively, it doesn't matter. Okay, what are the performance metrics? We actually have 2. And because some of them are related to the threshold, so we have the standard probability of false alarm and probability of kind of detecting the misdetecting the outliers. So there is this balanced accuracy that we have used. And in order to avoid this dependence of thresholds, we have also used the area under curve, which basically allows us to be threshold independent. So I'll have kind of perform, because for the methods that rely on threshold, we can actually show this accuracy, but then for the ones that don't have a threshold, we can show the area under curve as well. Okay, so let's now look at the results. First thing that I just want to kind of point out is that for, although we're using one particular architecture for both comparison, we have done some exploration for every of the 5 architectures independently. For example, this one versus all, we have kind of compared different architectures. For example, the size of the feature extractor, you know, how many parameters do we need, as well as in terms of binary classifier, how many parameters do we need? If you remember, here is the architecture, and then, you know, impact of number of parameters. So we have tested, we have kind of looked at the classification accuracy, which actually doesn't tell you anything about outlier detection. So there is outlier detection and classification performance that are impacted by the sizes. And here are the 4 architectures from this table. So what we learned is that architecture number 2, which actually in terms of feature extractor, having more parameters definitely helps. So this 151 is relatively a good ballpark of parameters for feature extraction. However, binary classifiers should not be very large, because we have learned that large binary classifiers are kind of for the outlier detection, kind of not a good choice, because they memorize the existing transmitters, which is good for classification. But then if you have unseen ones, which is basically outlier, then the performance drops. Okay, so now let's look at some other results. That is, how do we perform with respect to increasing the size of the authorized sets. Do we have 10 transmitters to authorize, 50 or more? So as we see, here is, for example, comparison on the one versus all and autoencoders. And we see that one versus all, which will be actually our most recommended approach, improves as you add more transmitters, because we have, I mean, the price is actually in the complexity, because if you remember, we're putting one binary classifier per transmitter. And these binary classifiers are learning only its class, and therefore they are not really learning much about, I mean, in contrast with autoencoders, which kind of, as you add more transmitters, the performance starts dropping. And our interpretation is that they're effectively learning signals, not really fingerprints. And they are not kind of differentiating this kind of, if you think about tightening the boundaries around authenticated transmitters, and therefore better rejecting the outliers. And another, this is again, area under curve, as well as the accuracy. Here we're adding also open max, and the performance actually kind of can be good, but it's complicated because of that threshold setting that you need to do, and it fluctuates for a larger number of transmitters. Now, if you remember, we have our hypothesis was that the training and testing has kind of huge impact on the performance. And this same day test is when we are training and testing on the same day. Different day test is we have 4 days of training, but then on the 5th day we perform a test. So what we notice, and this is basically the same set of classifiers with respect to the accuracy of one versus all, open max, and autoencoder. The same day we have pretty good performance, but then if you look at this, the trends are the same on a different day. Autoencoder degrades, fluctuation on open max, but then we see a drop. So there is, even for our best performing, we have about 10% drop, and that's basically, we think, attributed to channel variations as well as receiver fingerprints. Now we looked at also kind of what happens, right? Why are we getting this performance degradation? And turns out that actually our false alarm, this is now probability of false alarm versus probability of detection. So if you look at probability of detection versus same day, different day, we're actually not degrading. What happens is the false alarm for all of these methods, this is kind of solid is our baseline performance on a same day. And as you add, I mean, if you start testing on a different day, then your false alarms increases. So this is actually one problem that I think the community needs to address through new methods. Now, if you remember, some of our techniques are benefiting from, or we think would benefit from, the knowledge of known outliers. So here is now a set of architectures, one versus all, discriminator and D-class, that can exploit the known outliers. And here we're fixing the authorized set to 10 and increasing the number of known outliers. So we see that these techniques actually benefit from having some idea of what the outliers would look like. And we think that, again, one versus all is the best performing. And it, again, benefits from learning now, in addition to set A, from set K, and then we actually improve the performance further from where we were. If you remember, this is where 10 authorized, no known outliers, and we can push the performance with having some, let's say, 40 outliers in our data set. And again, different data, same trend, where we're seeing a performance drop. Now, we had explored, and this is just our initial, maybe not so elegant approach to overcome this degradation due to a different day test. If you remember, the detection same and different test was pretty good. It was the false alarm that we had to solve. And turns out we had additional data. So we basically increased the number of training days. If you trained 1 versus 4 days, this false alarm drops. So now the question is, I guess more data could show, although I would say that maybe we don't want to rely just on data as a solution to our problem. This problem could be reduced. Okay, so this is kind of our conclusion on the baseline problem of open set recognition. And as I kind of introduced, there are 5 approaches that we have considered. And some of them can benefit from this known outlier set. For example, OVA and discriminator and D class. And in all of these cases, having more known outliers helps. The difference between those, when to use which one, maybe this is kind of a design choice. If you want, if you have a label data set and want to know which one is the transmitter, these 2 architectures can also classify, while the discriminator cannot. If you don't have known outliers, again, you can use OVA and autoencoder and OpenMax. And within those, OVA and OpenMax can give you the labels for your signals or transmitters, and autoencoder cannot. So now the next part of my talk is kind of addressing this benefit, but although practical realization of these known outlier signals. So let's try to understand what the goal here is. In effect, I have shown, this is kind of my result from a couple of slides ago, that having known outliers will improve the performance. However, if I don't have a large database of signals from known outliers, I have limitations, or maybe I don't have any. Can I emulate or synthetically generate these samples so that I can augment data set and enhance outlier detection? So here is our problem statement. I mean, our database will always have a set of known transmitters and their fingerprints. That's basically our existing data set. And we know that this is our classifier that doesn't have any knowledge of outliers. So there is an accuracy. And we have shown that if I have known outliers or some outlier set with their samples, I can combine this and train my classifier and increase the accuracy. So now the question is, which set can I use? I might have only X, or I might have some set. So this is set O, but I don't have set O. I might have some partial known outliers which are contributing to this set Y. So we will look at actually 2 approaches. One is supervised, when I have some knowledge of outliers, and the other one is if I don't have any, so I'm completely blind. And we're going to basically ask this question of, can these emulated signals provide us improvement in the accuracy of the classified, open set classified? So how do we generate new signals? Well, we know that autoencoders are actually the way to go and reconstruct signals from, use your input sample, encode, and kind of generate samples through the decoder network. However, what we want is actually new signals. We don't want to reconstruct signals that we have trained on. These are our authorized sets, so we already have them. So then another approach is to actually use variational autoencoders, which are learning kind of these conditional probabilities on our input signal. And they will allow us to not only reconstruct, but basically sample signals from these distributions, okay? Now, again, and this is going to be actually our way of using our existing data that we have, let's say some subset of known outliers to create more. So how are we going to do that? I'll first talk about the supervised outlier. My apology, my slides are going into, okay. So, so if we are using a supervised outlier generation, that means that we have a set of known outliers, but we want more. So if we are using this variational autoencoder, which would basically mean that you train your variational autoencoder on a set Y, which is the known outlier, but very limited. You isolate decoder, and then you emulate outlier samples. Now, what is the problem with this approach is that you don't really have an idea of which transmitters are you really generating. Are you generating more that look like one outlier or another? So there is basically this problem of disproportional kind of samples from each set. So now we have actually proposed to use a conditional variational autoencoder, because we can actually have this additional input and decide which particular transmitter we want, so that we can have some sort of a balanced set in terms of if we need n samples, we will generate n over k samples for each transmitter. So this is our result. We have tested again one versus all architecture. That's our best performing, similar to what I've shown you with 10 authorized transmitters, and testing with 30 outliers, unseen outliers. And here I'm synthetically generating outliers. So if we don't augment our data set, this is our performance. And then if I use variational autoencoder, this is the blue one, and we see that the conditional one is actually giving us the best performance. This is again using a very limited data set for the known outliers. Okay, so now the second part is, what if I don't have any outliers? Can I blindly generate outliers to basically help my classifier? So here we actually have two methods. So the first method is, we call it Ellipsoidal Method. So this one is now, if you remember, I don't have that set Y. I only have set of samples from my authorized set. This is the set X, okay? So now if I use my variational autoencoder to kind of to get my encoder and decoder, to train it basically to get the decoder network. And if I isolate the decoder, I can create basically a latent space representation of my known transmitters. So how does that help me if I have a latent space of my authorized? Well, I need to sample signals outside of my authorized set. So how do I do that? Well, we can basically, and this is our ellipsoidal method, we're kind of looking at latent space. And for example, this is just some hyperdimensional object. And what we're trying to basically say is, let's create an ellipsoid that is going to bound kind of where our authorized signals lie. And for example, you can use this Lohner-John ellipsoid that can be solved in closed form and find the boundaries in this ZX space. Now, what do we do now? Oops. So then we say, well, I need to generate outliers. So where are the outliers? Well, they're outside of this ellipsoid. So now I will kind of create a thin shell around this ellipsoid and sample the signals from there through my decoder network. So this is kind of my latent space of the authorized that I created. And then by controlling this parameter delta, I can basically create new Z's that should not be resembling my authorized signals. So here are some results on the ellipsoidal method. One of the key parameters is, what is the size of that ellipsoid that we are increasing, this parameter delta. So actually the performance is sensitive to that threshold, and there should be an optimal threshold that can kind of, if you make it too big or too small, kind of impacts your performance. And again, we're showing that, especially if you have a very small number of authorized sets, authorized transmitters, augmenting it with this ellipsoidal method is helpful. And we believe that this is computationally very inexpensive. You can generate a very large number of outlier samples. The only problem is this tuning of the parameters to get, and it's kind of function of your data set, and it's hard to find it analytically. Now the question is, what, I mean, there is another approach that doesn't require this tuning of the parameter, which is based on the optimization. So this is actually a method 2 that also does the blind outlier generation. So how do we approach this? Well, again, we're using autoencoder to get the networks EX and DZ from the authorized set, because that's the only set we have. And now we want to find new samples by finding basically from a latent space Z's such that they are sufficiently close from the encoder point of view to our signal space. But when we decode them, we don't want to resemble our authorized transmitters. So basically this is kind of conceptual. How do we actually solve this is by solving this optimization problem. It's an optimization method. So this is some distance between our authorized signals and the new samples that we want to be minimized. And then we're training our new classifier to basically, for the sample Z, pick it from outside. Basically, we're adding in our classifier. So there is actually a classifier that we need to train. We add a new class in addition to our authorized set. And we want for that, for all samples Z to be outside of this class, samples. I'm going to most probably skip this. This is actually, we have a paper on this for details of the algorithm. But now let's kind of look at the performance. So here we have used actually Euclidean distance, just from kind of computational perspective. This was easy to implement, and cross entropy for training our classifier, that A+1 classifier. And here we have again tested it on smaller data sets, 71 transmitters. And we have used 10,000 samples of our known authorized transmitters and compared how the non-augmented data set and, augmented data set, so how much it helps. And again, we get the improvement if the number of authorized transmitters is small. When we have a larger number, the rate is, improvement is actually diminishing. And in terms of performance improvement, although I don't have it on the same slide, it actually gives better accuracy than ellipsoidal method. The downside is it's expensive in terms of computation. So here is kind of a conclusion on synthetically generating autoencoders. Again, the algorithm really starts with, do you have outliers, some known outliers or not? If you have them, then we have this method on conditional variational autoencoder, and you can generate and improve your performance. If you don't, then the question is, are you limited by computation and power? If you are, then the ellipsoidal method is the one that's less complex. If you are not, then to get a better performance, you could use these optimization methods to emulate the outlier samples. For those, you need only you have your authorized signal samples, and that's sufficient. Okay, so in the last part, our third kind of topic is a little bit of a shift. It's trying to address this problem of dynamically changing authentication sets. So let's see what, so we have considered basically so far that we have a fixed set of authorized transmitter, both in training and testing, and that doesn't change over time. But in real life, we need maybe to remove some transmitters or add new ones on the fly. And now based on the networks that I have shown so far, because they're all kind of based on deep learning, we would have to retrain. And potentially retraining will cost you some time as well as complexity. I mean, you have to most probably, you cannot train it, I mean, maybe on the authenticator or kind of send it at a more computationally powerful servers. So now the question is, can we minimize this off time and propose something that can be used in this intermediate time until you could train new classifiers? So here's just kind of to remind you that if you want for these existing approaches that we have looked into to add a new transmitter, then you have to, I mean, this part is actually something that we can reuse, but then you have to retrain this binary classifier for adding new transmitters, as well as if you are removing them. Basically, this has to change. For the D class, similarly, if you are adding, then you have to add this kind of classifier needs to change to add whether you're authorized or not. And for removing, that's actually easy because you're still recognizing and you can basically just say, fine, you're no longer authorized. One versus all, again, you need to add new classifier blocks. So basically, actually, orange here is adding what you really need to retrain. And for removing, it's fine. You don't have to do anything. So where is our inspiration? We're actually kind of now using partially deep learning, but also using this kind of information retrieval idea that you can kind of retrieve similar objects from a database based on some feature descriptor or some vector. So basically, if we can represent each of our transmitters through a descriptor vector in some low dimensional feature space, and that's basically where the neural networks are useful because they can give us these features of our transmitters. And then we are kind of building this database now that hopefully we can search very quickly. That's kind of one of the challenges that we'll try to address. So the idea is that we find our transmitter based on similarity and through a query of an object in a database. And for example, one of the algorithms would be nearest neighbor search, which again might have some complexity in large data sets. So again, we're using neural network. So we take samples, we do the features, and then these flattened outputs are our feature extractors or feature vectors. And then nearest neighbor can basically say, does it exist? If it doesn't, then it's not authorized. If it exists, then you can check whether it corresponds to some known authorized. So it's actually a very simple algorithm. However, the problem is that doing really the exact nearest neighbor would be very time consuming, and we want to have real-time latency sensitive kind of authentication. And therefore we think that using something like approximate nearest neighbor algorithms would be more appropriate. So now how do we implement this is basically using this hashing approach. And the idea is that you have these hashing functions that are putting each of the feature vectors into one of these buckets. And then your kind of algorithm is searching for, based on the hashing function between the two. So now which function to use is based on kind of what we want to do here, which is authentication. And therefore, we're going to use this locality sensitive hashing function. We're using kind of idea that inputs that are similar will receive the same hash value with high probability. And as I said, this approach is again also very simple. If you want to add new transmitters, we need to just add them into our database, their features, through this LS hashing kind of metric. And then removing is again very easy, no modification necessary. Here is kind of result that kind of shows the comparison between the classes that we have, sorry, the one class of classifiers, D class, which is just a simple authenticator, doesn't, classifier, not the authenticator. D class does the discrimination and classification. It can tell you whether this new transmitter is a particular one. And then we have different LS hashing approaches based on kind of straightforward or using some dimensionality reduction on the feature extractor using autoencoder. or using a very small number of samples in our LS hash to build these buckets. And we see now the new metric is, if you remember, we want to do real time. So it's really the question of time to retrain, or basically adapt our LS hash versus retrain D class. So as expected, D class would require long retraining time, while adding these new transmitters is going to, I mean, if you are just adding samples, it's the smallest. If you need to do some autoencoding, you have to pay the price, or this is the full LS hash. And in terms of performance accuracy, as we are adding this, it's again, good accuracy that we can achieve with these LS hashing methods. And in terms of not only retraining time, but the complexity. If you remember, the whole motivation for LS hash was, I mean, LS hash was actually having the longest, but with these dimensionality reductions, we can actually get comparable to a D class, which would be fast, but again, slow to retrain. So we believe that this LS hash is on par in terms of outlier detection accuracy, but much better retraining time. And one kind of idea that we would like to propose is that you use it while your D class is being trained. If you start adding more transmitters, you can take some time to really retrain your D class, but you don't want for your network to be down and you still want to authenticate. So this is kind of the idea that the LS hash can quickly give you some intermediate performance until you get the new classifier back. So this is kind of the terms of availability. Sorry. Okay, so this is in summary kind of what we have covered in this talk with respect to OpenSet RF fingerprinting for transmitter authentication, and kind of explored, you know, what are the deep learning techniques that we can do, we can use to solve different types of problems within this OpenSet recognition, as well as address data augmentation effectively and real-time performance and some alternatives to get that. In addition, I would like to actually advertise our data set. It's actually coming soon. We're by the end, we decided to call it VISIC 21. Stay tuned, and 21 is actually, it's going to be released by the end of this year. If you remember, so far we have increased the number of transmitters. So this is 174 Wi-Fi transmitter. We believe the largest data set of RF fingerprints that is going to be publicly available. And I haven't shown the results, but I showed only one receiver. We have enhanced our data collection with 41 USRP receivers. Again, same capture, same kind of variability across days. In total, 10 million signals that will hopefully enable a large-scale transmitter authorization research, closed set, open set, any way you want to use this large transmitter data. And what's, I think, nice about this, it also captures impact of channels, because these are kind of physically placed in a different environment, captured over different days, as well as because we have multiple receivers. We are now seeing, or actually we have some preliminary data that will come in with the paper that is going to accompany this data set with impact of RF receiver fingerprints. So if you're really interested to dig deeper into our work and results, here are the papers that the two of them, one GlobeCom early December. This one is actually accepted in DICEPAN, but you can find it on arXiv, and TCCN paper, the first work. Thank you all for your attention. I would be happy to answer your questions.
Thank you so much, Danijela. This was really a wonderful talk and very wide set of questions that we have that are awaiting for us. So I will start reading out the questions. The first one comes from Shubham Chakraborty. He's saying that Dr. Cabric, based on the testbed structure, except the elevation angle, the channel properties are expected to stay same for all training and test data. Will different channel properties have considerable effect on the result?
Okay. So you'll see this new data set. You're right. Like in terms of static, the geometry of this is not changing. And we're the receiver. Okay, so the receivers are at different locations. Okay, and for those of you who are familiar, this is actually a fairly large room. So the spatial separation between the receivers will actually account for different channels. Okay, so every receiver will have a different channel. In addition to that, what we have noticed, and keep in mind, this is a Wi-Fi. Okay, now we need to most probably understand better what has happened. We have done this actually over a month. We did every capture, within a day, and then skipped a week and so forth. So the environment, which is again, Wi-Fi channel, could have had some background interference. So that's kind of one additional problem, as well as what I'm pointing out here, that the receivers are also having their own fingerprints. So this new data set that you will see will definitely have, we have done some initial work that you will see again in the paper with doing channel equalization. And if the hypothesis is the channel doesn't change, you should get the same channel all the time, which is definitely not the case.
Great. So the next one comes from Mohammed Shahmir Omar. Dr. Cabric, when you test performance of OVA and autoencoder versus the number of transmitters, is the neural network retrained for different number of authorized users?
Yes, I mean, it has to be, right? OVA needs to have a binary classifier for every time it's retrained.
The next question comes from Amir Hussain. How does the performance of the classifier change when it is tested on IQ samples received from another receiver? I think this is the question alluded towards the receiver fingerprinting.
Yes. Okay. So as I said, stay tuned. This is actually a very important problem. We have seen that if you train only one authenticator, and then you have this authenticator is trained, let's say, for all transmitters, and then you apply it to the IQ samples from another receiver, there is a significant performance drop, like to the level of below 50%. So there is a huge drop, yeah. Okay, I'm not sure if I want to give away. As I said, stay tuned. The paper is really coming soon. And again, the solution is not very elegant, but it works so far. Given 41, increasing the number of receivers that you use in your data. That's the reason these 10 million signals will definitely help. But the question is, from the practical point of view, what is sufficient, right? And to me, actually, ideally, I would like to do something more on the calibration side from the receiver so that we can disassociate the RX fingerprints from this, yeah.
Sure. The next question comes from Michelle Kulhandijian. Is the IQ dataset based on time series or demodulated? Do you perform any data augmentation since there are channel impairments on the different days training, etc.?
Okay, so well, we use USRPs. Okay, so although we have Wi-Fi transmitters, the receivers are we are activating one at a time. So let's say this receiver takes 1 second of IQ samples, and then we do post-processing. Basically, we're trying to isolate packets and capture the preamble, and that's all. So these 256 samples that we are using are start of the packet and preamble. And the reason why community will be able to use any portion of these IQ samples over 1 second, but we believe that preamble is a kind of a common signal for all these Wi-Fi transmitters, and the networks are then kind of trying to not deal with randomness of data, but just randomness of the signal. We have a prior paper, ICNC 2019, where we studied, impact of different modulations and different signals versus having the same data, basically asking each transmitter. Here it was easy because it was Wi-Fi, so we already knew that every Wi-Fi packet starts with the same preamble. But if you are dealing with some other systems, having the same data is beneficial. Now, features that are not IQ samples, we have explored in other work, but here we kind of went raw IQ samples, because even from our prior work, we kind of showed that. And I think from the kind of body of work that we have read, IQ samples are the good feature actually to start with. Yeah.
So I understand that there's time domain signal. And have you seen any difference, or have you looked into whether if we do an FFT or move it to the frequency domain, if it changes the performance at all or not? Or in other words, whether it's the features are truly in time domain, or there are other features that are in frequency domain?
As I said, in this prior work, we have done the analysis and shown that IQ samples are as good as this other feature. It was like a FFT magnitude and phase, and others. But for this work, my student has tried, and he kind of, after a quick analysis, showed that IQ samples and FFTs are as good. But I would say one is welcome to explore any transform prior to these neural network type of feature extractions. Yeah.
Sure. So I see Marwan is raising his hand. So please go ahead. I will read the next questions later on.
Thanks, Danijela. Yeah. Very interesting talk. I have a general question. I have lots of detailed questions here, but I guess my initial understanding is you're trying to authenticate fingerprint for the purpose of authentication. And that tells me that you're trying to identify individual transmitters. But I get the impression is that ultimately what you end up with is identifying whether the transmitter belongs to a group that is basically the authorized group or not. Mm-hmm. Is this correct?
Yeah, actually that's where I started from. I'm not sure if you, let me just try to find that page. Yeah. So here is kind of the differentiation of problems. I'm sorry. We're just going to a full screen mode. So this is kind of what, we have authorized, we have outliers. So this is some kind of space where if you're classifying, you're trying to basically say the colors, right? Or you can call this transmitter 1, transmitter 2, 3, and 4. Now, if you're building a classifier that only knows about these 4 transmitters, if any new signal appears, you're going to treat it as one of your classes, and that's a problem. So then we said, what if you build a new type of algorithm that does the anomaly detection? So now you are saying, well, I have these circles are basically saying, this is my authorized set. I might label it, right? Or I don't have to. I can just say, if you fall in one of these regions, you are authorized. If you're outside, you are rejected, right? And then this last one, which not every, I presented 5 approaches. The last approach that I showed is kind of doing, building a boundary or trying to recognize each transmitter individually, while at the same time saying that if you don't fall into these boundaries, you are not authorized, meaning that you're.
I see. So it's the last one, the open set recognition is the one.
Yes.
And that would be kind of, I guess comparable to say using, for example, CFO-based type of fingerprinting. This is kind of the common technique that people use to identify using physical layer attributes.
Yeah.
Okay. Thank you.
Yeah.
So the next question comes from Zhangqing Zhang. The first question, he has 2 parts of the question. What could be the possible reasons that the accuracies of different days are worse? And the second question is, will the Wi-Fi dataset be made publicly available? I think we have the answer for the second question, but maybe you can comment on the first part.
Yeah. So we have different days. So I have shown that we have a drop, right? It's not that we completely fail, but we drop in terms of the overall accuracy. And we believe that both channel and receiver fingerprints are changing over time, even in this setting. And again, this slide kind of shows that if you look at the detection, we're actually still detecting properly our class of authorized. Now we have the false alarm. And I think that's for the security problems an issue. And here we're basically seeing on different days, there is an increase for all of these networks. Okay.
The next question comes from Meng Li. What would be the impact of the dynamicity of the transmit receive in view of distance and channel environment due to mobility, etc.? So I think that's a generic question in a sense that we know that in orbit, it's basically a very static environment. And what happens if you truly use it maybe somewhere in a power platform? How different it will be?
I think that's definitely of interest to the whole community to have a mobile kind of data set. That means the transmitters are the same transmitters is appearing in different locations. I'm not, I mean, I hope that power platforms like Powder can help us with that. I mean, for us, as I said, having these different receivers is kind of, if you think of the transmitters are not moving, but if I measure it with different receivers, is that equivalent to the transmitter has moved? I mean, not exactly, because we also have the receiver fingerprints, but I think that it's also practically relevant. There is a body of work on the channel augmentation, right? So one can, because I would say in wireless community, we have a good models of wireless channels and mobility. So to me, maybe the first step would be to emulate different channels and augment data set and so forth. I think the hard part is on the kind of these real imperfections in RF hardware that, you know, I talked to my colleagues you know, who build circuits, and, you know, I mean, building a model is not really that easy, you know, because the variabilities come literally from manufacturing kind of point of view. But I mean, maybe going down to kind of a layout of a circuit, extracting and making variabilities and so forth. So that's kind of where I think we need still measurements from real radios. But for channel, in the intermediate time, maybe we can do some augmentation through to channel synthesis.
Sure. And something related to that is also what kind of signal to noise ratio is required to achieve these accuracies, or what SNR did you see in orbit?
I think these are fairly high signal to noise ratios, right? The room is not that large, and it's like a relatively high Wi-Fi signal. I mean, the noise of USRP radios is not the best, but I would say that SNRs are in the order of 10 and above, right? So it's not really low signal to noise ratio. Yeah.
That's great. So the next question also comes from Shubham Chakraborty. Dr. Cabric, in slide 22, you mentioned that autoencoders perform comparatively poorly, and the interpretation is it is learning signal instead of fingerprint. Does it mean that it is not learning the stochastic properties and not the does it mean that it is learning the stochastic properties and not the deterministic ones coming from hardware? If yes, how then the variational autoencoder help emulate additional known outliers, as latent space will still be expected to have both stochastic signal features and their hardware features coming from the hardware fingerprinting?
Oh, I think question. Yeah, so variational autoencoder is actually trying to, let's get to that. So that one actually uses, what's that? think it's here, right? So we have a subset of known outliers, which is relatively small. Maybe that's kind of where, if you look at actually autoencoders, there are, okay, keep in mind that when you look at the autoencoders here, it is as the size of the authorized data set increases, okay? Actually, autoencoders are pretty good with lower number of transmitters. And if you followed why am I augmenting is actually because I don't have enough known outliers. So the goal is to start with, the small number of, this is my, I have a small number of Y and I want to get more. And we believe that autoencoders on this small data set actually can have a good representation. And then we are kind of enhancing it through this ellipsoidal method effectively. So now, I mean, it's an interesting point. We haven't explored the size of the, as the number increases, what would be the, if the autoencoder has this, or variational autoencoder has this problem, yeah.
The next question comes from Zhengguang Zhang. There are two questions here. So how do you deal with the data when signals from multiple Wi-Fi transmitters collide? And the second one is when you extract features from the preamble, what features are you more interested in and contribute a lot on the authentication or recognition?
Okay, so the first question is, okay, so Orbit testbed is actually a controlled environment. So we had option of turning one transmitter at a time. And we knew exactly, we had labels and stuff like that. So there were no collisions, okay? And in terms of the data, as I said, we have done processing of these, finding the start of the packet, right? Through signal processing methods and extracting 256 kind of a preamble length that is common. There is a possibility that there are some timing offsets, right? That our detection is not perfect. We haven't accounted for that one. And as I said, I'm not showing the results here. We have done the channel equalization, meaning that because we know Wi-Fi preamble, right? We can do the channel estimation and effectively equalization to remove the effect. Yeah, so as I said, our prior paper has shown that having removed the randomness of the data from the authentication problem helps.
Sure. The next question comes from Michael Rice. Do you have any sense of what features the neural network are extracting from the IQ samples?
No idea.
Yeah.
No idea. That's kind of, I think that's where kind of we go back to the history, right? Where, I mean, I have worked on this as well, right? Where we're trying to build all sorts of, I mean, even your FFT kind of, even if you do that, you would still feed it to a neural network to do further kind of extractions of features that are transmitter specific. So honestly, I don't think we know. And I'm not sure if, I mean, in other domains, I'm not sure what if you always know what you're learning, right? You just let the neural network learn what's the best for your performance. Yeah.
Yeah. The next question comes from Oritra Day. Dr. Cabric, in the process to classify transmitters as authorized or not, what is the intuition to use outliers for enhancing the accuracy?
Mm-hmm. So basically our intuition is that if you look at these kind of tightening the boundaries around our own authorized transmitters, if you have some, I mean, all these methods that can benefit, right? Discriminator, right? It's effectively, if you have known outliers, these are the ones, they are kind of helping tighten the boundary around authorized, right? Because in this feature space, if you didn't have, let's think of this as known outliers, not as an outliers, right? These boundaries could have been much larger if I did not have the known outliers. As soon as I put more outliers that are known, my network should learn how to tighten the boundaries. And that's the reason these augmentations are kind of going after that idea of ellipsoid, right? And, you know, although outliers, you know, I think, you know, we kind of started with this idea of, you know, the number of possibilities is infinite, right? It's really what we think is a security threat is that in the feature space of a classifier or a neural network, that there is a signal type that is very close, right? So from our Wi-Fi network, I mean, how do we know it's close? Well, when we are building our data set, right, or using our data set, right, you know, our known and outlier are all Wi-Fis. So it's kind of by the design, we're picking signals that we know are similar, right? As opposed to, you know, getting IQ samples from, you know, another signal in the same spectrum, right?
예. 지금 그 세미나가 끝나서 전화드렸는데, 저 이명.
Sorry about that. So the next question comes from Amir Ashtari Gargari. Thanks for the nice presentation. What is your idea with regard to using active-passive relays in communication? The RF fingerprint, I think can the RF fingerprinting work here?
I'm not sure I can answer to that question, but I think that the RF fingerprinting is, you know, I worked in spectrum sensing and signal classification for a long time, and kind of inferencing about, you know, some specific kind of signal types is always helpful. So now, not relying on higher layer protocols to tell you something about the particular transmitter, I think can be beneficial in all sorts of applications. I'm using security, possibly relaying or many others, right?
The next question comes from Alessio Skelling-D. Thank you so much for the presentation. What kind of neural network architecture has been used in the feature extraction block?
Which I think it's
15 or 15?
I think it's 15, right? So this is the feature extraction. It has residual layers and then a convolutional layer. This is actually all in that paper, journal paper at DCCN, where you can read more about it.
Sure. The next question comes from Syed Shirazi. How does the SNR vary amongst recorded data set? Do you do some offset correction as pre-processing?
No, we don't do correction of the SNR. I mean, we believe that, I mean, there is SNR variation for sure, but we don't correct for that. And then offset, I'm not sure which offset you are. If you're thinking about frequency offset or anything of that kind, we don't.
Okay.
No...
Yeah, I think the question is written in a way, I believe that the first part is on the SNR, the second part is on the carrier frequency offset correction part.
Yeah, we let SNRs be what they are, and then we don't correct for frequency offset. I mean,
yeah, but I think the question was the SNR. How does the SNR vary? Do you have data for different SNRs, or is the same SNR?
Oh, it's the same. It's the same.
I see.
Yeah. I mean, it's actually not the same SNR. What's the same is that these Wi-Fi's are behaving in the same way. We don't control their power. So basically, right, the resulting SNR is just what happens if you put transmitter with the same power at you know, and measure it at the receiver at a certain distance. We don't play with power levels on each end.
Sure. There's a two-set question coming from Hang Hu. After your classification model training is done, the model will reject all new transmitters as open set recognition. Is it reasonable because some new transmitter may not be malicious? And the second question comes again, why don't we use the GAN network to generate outliers? VAE seems not as good as GAN when generating negative samples if we have some known data.
Okay, so part one, I'm you know, the motivation for who are these devices outside of our authorized set, they don't have to be malicious. I agree with you. They can be, any secure network or private network can basically have limited access or privileges, right? This authorized could be high priority, high privilege. You can frame it in any way, as long as you want to differentiate among them. Okay, the GANs, we have actually attempted to use GANs. We didn't have success. And actually I have some other collaborators that have shared the same experience. I'm not saying that it's not a good choice. What we have accomplished did not show us good results. Yeah.
The next question comes from Xu Wei. Again, there are two parts of the question. Is there a way to distinguish between known data of different days and outliers if they are all classified as unknown classes? And the second part is, if outliers are disguised as known data, can they be detected? I think the second part is more towards spoofing annotation.
So yeah, no, I'm not quite sure. And the first part is to kind of enhance the way we're classifying to understand that data comes from different days. But still, the problem, I don't see how that solves the problem eventually, because at the end, you still have a limited data, right, of training. And then at the end, your system has to run on a new day. So how is this, what you have differentiate from your training data, that it's a different day, right? How is that going to help you in this new day? I'm not quite sure I understand the question.
I think the question is that whether there is a way to distinguish between the data on different days or whether they are being classified as outliers. So when the accuracy goes down on different days, I think it will be classified as outliers.
Mm-hmm. I mean, the way we classify, we don't have that feature, but I'm wondering if, yeah.
I think we can take it offline for this. Then the next question comes from Hisham Mohammed. Thanks for the great talk. How do we consider the physical layer authentication as a practical approach to achieve integrity? However, the received signals are the aggregated effect from transmitter, channel, and the receiver. However, we need only to check the transmitter.
Yeah. Great question, right on the spot. I think that's what the whole community needs to realize. And I think that's, as you said, 3 transfer functions, right? Transmitter, fingerprint, channel, and the receiver. We only care about the transmitter. Now, what are the tools that we can use from understanding that some of the features are really due to the channel, right? And how can we build networks that can either remove, correct, whatever we can do. Maybe even, as I said, we tried channel equalization, for example. And then I think the receiver fingerprints are, to me, a harder one, because the way we don't understand transmitter fingerprints is kind of almost even more difficult on the receiver. I don't know if you follow, like many agencies that are funding research. I mean, RFMLS from DARPA is most probably the most prominent one in the US that I know of. But other agencies are now trying to understand, what type of receivers do we need to build, right? If you kind of pose the problem here, these are my relatively cheap or someone that I don't have a control, but the intelligence is here, right? So I'm right now solving the problem with deep learning, but we might need to invest in the hardware as well, right? So that, I mean, this cannot be cheap, right? If you really want to do a secure system. And now the hard question is, what should this receiver do, right? What kind of performance specification should it have so that I can differentiate my own fingerprint? Should I be very good, or should I have something that is very obvious that it's not due to, when I say very obvious, not to me, but to the neural network, that this is something that comes from the receiver.
Sure.
I mean, great problem, great question, great problem. I think the community needs to understand that. As I said, from the channel perspective, understanding how to augment. Again, throw more data at the problem is possibly a solution, although I don't personally like it as much. Yeah.
I think it was a great talk, and overall, our community definitely needs to understand how we can utilize fingerprinting in different ways to sort of have this fingerprinting as a mode of authentication for specifically for IoT devices, because they will not be able to do all the different kinds of encryption system that we are familiar with. So
this method can be, I'm not sure if people who are working in security most probably are panicking when we talk about this. So it's not the only security measure that we most probably need to rely, but I think it can be a great supplement. And I think what's nice about it is that this deep learning and more general AI techniques can be helpful, right?
Absolutely. So as we move from static transmissions or one device transmitting the same signal over and over again, we might end up having a more dynamic system in future. Like the transmitter will be transmitting more different kinds of signal, not just Wi-Fi or not just LTE or not just LoRa. So in that sense, how do you envision the architecture and how do you think that the research is going to change for that?
I think there are two sides to that question. One is, do we need to recognize what the transmitter is doing and then apply a classifier that's the best for that signal type? Or we know that, there is also I haven't tested that idea, but if we find that certain types of signals are best exhibiting the transmitter fingerprints, right? That might be the way to, if you want to be authenticated, I actually want for you to do something where you're going to show your face, right? So for example, if you're all that's kind of my idea that, as I said, we haven't explored, but we know, our early work has shown that many of the fingerprints come actually from the power amplifier nonlinearities or some spurious emissions. And then if you transmit a certain type of waveform, these behaviors are going to be showing up much more prominently than if you're doing something that's easy, QPSK modulation, right? So that's kind of, I think there is a connection between types of signals. Most probably I send a message of, Wi-Fi preamble is the way to go. You're right. I think that for Wi-Fi authentication, most probably it's a good one, but for more general one, if we have the flexibility, can we find a way, what is the best waveform that we can authenticate? Or if the transmitter is doing something unwillingly, right, we just need to verify it's doing its own adaptive modulations. How do we then put these two things together, right? Or maybe out of the set, again, pick the one that is showing or cross. Lots of interesting problems, I would say.
Sure, absolutely. I have one more question coming from Said Shirazi. How far do you find us from deploying deep learning-based classifiers into live air signal classification?
Wow, that's the toughest question. I hope I could. The community is actively working on this. Industry, we have lots of industry collaboration on this. I think that we're making progress, but in terms of maturity, most probably not this year or next. But okay, if I can just put a random guess, in 4 to 5 years, I think this will be possible. Given the number of people, industry, and investment from different agencies in this problem, I think we're on the verge of understanding. I want to say it's going to be a universal tool, but we're going to find the application domain where these techniques can be safely used, so that we have trust that this is deployable.
Great. So Suba, do you want to make this announcement that I see over here in the chat?
Sure, yeah, it sounded like someone again had a question about whether we'll have the slides available. Yes, it will be available, and as will our the entire video recording of the talk will be available on the YouTube channel. So I'm just going to copy paste the link for the YouTube channel in the chat in case someone wants to, keep it And
I will
thanks, Danijela, for
the PDF of slides right now, so you can actually post it. Yeah, you should have it. Yeah.
Sure.
Thank you so much. Thank you for this wonderful talk and discussing all the important questions that the community has, and probably we will lead to a better solution in years to come.
Yeah, and honestly, I feel that with this data set, where a lot of people most probably have great ideas, but unfortunately for this type of research, you need to have the data. And yeah, we're looking forward to seeing more work on this topic.
Yes, the data set is very much appreciated, Danijela. And thanks also for giving us this really great talk.
Well, thank you
and
so
thanks
much.
to all the audience for your engagement and your questions. Hope to see you next month, I think.
Bye.
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 So by the way, I have the links for the SIG site and for the YouTube channel. Both are up on the chat if anybody wants to take it. Thank you. Bye.
Thank you. Bye.